Our last example is space-time translational invariance, and it is defined on the coordinates, on the space-time coordinate itself, where A indicates the direction of the translation. So for instance, if only A naught is non-zero, we will have a translation in time, but if we have A naught equals 0 and the space-like component non-equal to 0, we will have a translation in space with a given direction of the Euclidean vector. And the magnitude of the translation is given by lambda. So let's assume we have only one real scalar field. To apply Noether's theorem, we need to determine how the field transforms under this space-time translation. The function phi is unchanged because it's a scalar field. That means that it's a Lorentz scalar. It takes it's the same function in all inertial frames. However, the space-time position is changed by the translation. Therefore, we need to connect phi of x with phi of x dash, and we need to do that in the case of an infinitesimal space-time translation. So we need to Taylor expand and just keep the first order in lambda. So this is our delta S of phi. And we now do the same thing for the Lagrangian. Not that the Lagrangian is a function of the field, but the field itself is a function of space-time. Therefore, we can write the Lagrangian as a function of space-time and Taylor expand. So now the Lagrangian is changed, but because mu is a constant, it can be put inside the derivative, and therefore we have just a change of the Lagrangian, which is a covariant derivative of a function of space-time. So we now have all we need to express Noether's current. Notice that we didn't specify an expression for the Lagrangian, so this discussion so far is very general. And this means that we will keep this term as it is. However, we can replace delta S phi and f mu by the expressions we just obtained. Note that we used nu instead of mu for the expression of delta S phi because it's a dummy index. I would now like to factorize by A because this is a choice of the physicist. We choose which direction we want to translate in space-time, whether it is in time or in Euclidean space. And for that we will rewrite this term using the metric. As we have nu with a lower index here, we need to lower the index here, and that's easy because we know that when we have a function with a contracted index, we can lower one index and raise the other one. By definition, we call this term between brackets the energy momentum tensor T mu nu. So we see that our conserved Noether's current J mu is A nu times this energy momentum tensor T mu nu. But again, we can choose A in any of the four directions in space-time we want. So we have, in fact, four conserved charges defined for different values of nu equals 0, 1, 2, or 3. If we have a translation in time, we have nu equals 0, giving... By definition, the term between the brackets is called the Hamiltonian density, while the derivative of L with respect to phi dot is the canonical momentum of phi. These expressions are the analog of the definition of the Hamiltonian and of the canonical momentum in classical mechanics. So this conserved quantity associated with symmetry under time translation is nothing else but the energy of the system. And if we now consider a translation in space instead of a translation in time, we get three other conserved charges, which are the momentum of the system. And we have three of them because there are three directions in space. Remember that the covariant derivative is naturally lower, so that's actually minus the derivatives in space. Therefore, if we were to express that with a Euclidean vector, we will have minus nabla phi. And finally, because the metric is diagonal, this term has to be 0. So our general expression for the Euclidean momentum becomes, where we have used the expression for the canonical momentum of the field.